management and public communication. The name of Meteorology and Geophysics Academy before AMG. Its campus it is at the Bandung Institute Technology ITB in ITB Bandung, and from 1960 AMG was moved to Jakarta. Moved to Jakarta, its campus was in office of the Meteorology and Geophysics Institute (LMG) in Arif Rahman Central Jakarta. And the year 1960 until 1978, AMG under the Center of Meteorology, Meteorology and Geophysics, and 1978 AMG changed the name of the Meteorology and Geophysics Education Training Center BPLMG to the AMG. Since and until 2004, AMG remained under the Education Training Agency with degree of the Minister of Transportation. Before the AMG is under the Minister of Transportation. And January 2005, AMG under the Meteorology and Geophysics Agency BMKG. Okay, AMG. And 2040 was history year of the big family of STMKG because the year of president regulation of the Republic Indonesia concerning the change of the Academy Meteorology and Geophysics AMG to the college. Jadi the college atau STMKG removed from the AMG in 2014. Okay, next. Now, the STMKG is one of the technical implementation unit with Meteorology, Climatology, and Geophysics Agency. The STMKG under the BMKG. Led by director who is assisted by 3 vice director. Has four study program, namely applied because bachelor in the field of meteorology, climatology, geophysics, and meteorological climatology and geophysics instrumentation. Jadi we have 4 field in the STMKG: meteorology, climatology, geophysics, and instrumentation. Instrumentation for meteorology, climatology, and geophysics. All study program have been accredited by the Indonesian Higher Education National Accreditation Board. Okay, lanjut. Nah, yes, the structure of the BMKG, the Senate, the acting, the director, and then the Puket Pertunawan, etc. And we have STMK have 4 program study. This is 4 program study diploma for geophysics, climatology, meteorology, climatology, geophysics, and instrumentation BMKG. Okay. But until June 2023, we have the assistant ahli or lecture. Lecture is 8 person, and then the assistant professor 38, and associate professor 7, and professor 0. We have Pasuko. Next year the professor. For the education, master degree 40%, and for the doctor we have 11. And then the lecture from STMKG to study in the other university for the doctor. Okay. Okay, and then the human resources to students until June 2023, the methodology total is 3,000, and climatology 86, and for geophysics 108, and instrumentation 3,013. Total is 100. The instrumentation, the student is very big from the other the program study, because we need the personnel to technician for the instrumentation, meteorology, climatology, and geophysics. Okay, lanjut. The Stockholm accreditation from for study program national meteorology is very well, and climatology very well, geophysics accreditation very well, and instrumentation good. Okay, okay, lanjut. This is the certificate accreditation. Okay, lanjut aja. We have the SMKG, we have the laboratory for meteorology, climatology, geophysics, and instrumentation. This is the facility in the other, and the like is from the facility meteorology department. This we have the satellite, automatic weather station, GMS, synergy, etc. Okay. Now, for meteorology observation tool, we have the garden observation, etc. Evaporation, solar radiation, evaporation, rain gauge, and thermometer maximum and minimum. This is the temperature. Okay, lanjut. This is for facility climatology department. We have computational climatology. We have under the first stage, we have the computational climatology. And next, and then the facility for the air quality equipment. We have for air quality equipment, and then next, this is laboratory facility geophysics department. Like this, we have the SESCOMP, we have the intensity meter, and lightning detector. Okay, next. We have all GPS mapping and resistivity meters. Okay, next. Portable seismograph and seismic array. We have, okay. Gravity meter and GPR. And then the laboratory facility instrumentation department. Okay, we have the CISCO, the CISCO Networking Academy Laboratory, provide learning about networking, cyber security, and infrastructure, automatic, etc. Okay, lanjut. This is we have engineering system laboratory, electronic laboratory, computer laboratory, and geophysics calibration laboratory. We have for all the geophysics. Mechanical workshop, this one to 3D printer, spot, PS short period, etc. Nanometric trillium. We have this one. Okay. We have universal turning and milling machine, DC, AC power supply, welding machine, etc. Okay, lanjut aja karena banyak. Microcontrol trainer, electrical hand drilling machine, precision Super X 910. Okay, electrical precision machine, hand roll machine, a painting shop. Grinder, etc. Air dryer, table. Okay, we have the plan to future. We have the future from the STMKG is lanjut. has for professor. We need we have yeah we hope the has the four professor, and then all accreditation excellent study program. We yeah we hope the accredited excellent study complete laboratory. Yeah, we have the complete laboratory from the instrumentation and geophysics, but for meteorology and climatology, we need to explore again for the instrumentation, no, for the facility in laboratory meteorology and climatology. Complete laboratory and has competency certification institution. Yeah, we plan to candidate for Taruna after the uh, successes in the lecture, we we need to Taruna has a certification competency, yes, and then minimum 5 region cooperation we need because it is very important for collaboration or cooperation with the other university like the California, I said, and etc. And organize postgraduate program accept in international student. Yeah, we plan this one. Okay, lanjut. Nah, uh, uh, we plan also STMKG as a state-owned or government college that belongs to BMKG. And then STMKG is highly a selective college with an acceptance rate of around 2%. And STMKG have specialized knowledge and skill in the field of meteorology, climatology, and geophysics. And then STMKG has a strong alumni network which can provide graduate with support and working opportunity. Ya, oke, lanjut aja. Field practice and in class like this, for the student, for the cadet, we have this one 4 years bachelor program. We have a program for years bachelor and tuition free institution. Yeah. In lecture in here, study in STMKG is pre-institution. STMKG graduates are guaranteed employed by the BMKG. Yes. Good. Yes. Okay, lanjut. This is cooperation to foster collaboration. Yeah, we plan to cooperation with the other university or laboratory in the world because like the excellent in training and research. Fully equipped laboratory, we will open the international student by 2024 and 2025. I think the start with the electric Timor-Leste, etc., Brunei, etc., Papua New Guinea, we hope. And then, sorry. Tadi, sorry. Enggak, belum. Pencet tadi. Sebelumnya. Okay, sorry. Yeah, collaborate on, we hope the collaborate on observation, analysis, and publication of damaging earthquake and tsunamis after the official release from the Meteorology, Climatology, and Geophysics Agency, and then student exchange program, yeah, and then joint research project atau research collaboration, sharing of research and facilities, curriculum development and quality assurance, faculty staff exchange and visiting researcher program, and conference and scientific events. Yeah, this is the cooperation to foster collaboration. Yeah, we have the collaboration because the BMKG is member of the WMO, etc. Okay, thank you very much for Prof. Herr Horacio Faris.
Thank you so much to Mr. Dr. Andes Mamas dari Seman DEA for the introduction and playing for SMKG opening remarks. And now, without further ado, to begin our session, allow me to invite the moderator for today's event. Please welcome our moderator, Mr. Dimas Salomo Januarianto Senipar, PhD.
Okay. Thank you, Anggun and Pak Maman. And before I start, I want to increase our attention first. If I say hello, you say hi. If I say hi, you say hello. And if I say STMKG, you say Jaya, Jaya, Jaya. Understand? Okay? Hi. Hello. Hello. Hi. STMKG. STMKG. Okay, thank you. And welcome to Professor Horacio Faris. Okay, this is our proud STMKG. We are very proud to be part of the STMKG. And let me introduce Professor Horacio Faris first. Professor Horacio Faris is a professor of the applied geology at the California State University, Stanislaus. He is actually a geological engineer by training and with a degree from the Mexico National University in engineering and with the master and PhD degree from the Stanford University, one of the best universities in the world. He is also a professional geologist and certified engineering geologist in California. And what's very interesting that Professor Horacio also wrote some books. And if I look in the internet, he wrote 2 books in the foundations of the environmental geology and in the notes for the California geology, which you can download it freely in the internet. So it's a very good resources for the students to study the geology. And today, he will give us the lecture about the earthquake geology, contrast between California and Indonesia. And Professor Faris. And you will have 1 hour lecture followed by Q&A sessions. And floor is.
One, two, three. Yes, this works. Where do you want me to stand? Here? Facing that way? Okay. Salam alaikum. Hola. Good. You need to start learning Spanish. Spanish is a fun language. Plus, you can travel half the world with Spanish. So this is very good. Okay. Can we have the first slide, please? So my name is Horacio Ferriz, and I am a geologist. So I'm a little different than what you folks are. Next, please. Okay. I am interested on the Earth, the whole thing. Now, I do have interest on that. Planetary interiors, that's where you come in. You geophysicists, you can see into the Earth. We cannot. The type of work that your instructor is doing with seismic tomography is of great interest to me. No. It's of great interest to me because I'm interested in planetary geology. I do like to kick rocks. All geologists look at rocks, right? So the solid Earth is of interest to me. But in particular, I'm a hydrologist. So I'm interested on the water, that beautiful part of the Earth that is blue, that's my specialty. So I'm interested in the oceans, in the rivers. And of course, it doesn't work if you don't have the atmosphere, because the atmosphere is the vehicle for the hydrologic cycle. So I have great interest in meteorology as well. I know quite a bit about it, not as much as some of your meteorologists, but I know a fair amount about it. I come from Mexico, which is right there in the center of the world. And Mexico has many similarities with Indonesia. It's a mountainous country. The north is dry. You don't have that dry part. But the south of Mexico is equatorial, subtropical. So we have lots of tropical conditions. Our weather in the south is tropical. Because it is very mountainous, it's very difficult for infrastructure to develop, similar to Indonesia. You know, our roads are left and right and up and down, and that makes for difficulties in development. I'm an old geologist, which means I have many interests, and when your professor was describing your instrumentation group, I'm like, oh, I want to work with an instrumentation group. I need a probe that I can design to study Lake Toba, and in that way, when I come in research exchange, I can go to Lake Toba and have some go at it. So we have some points in common. Professor De Currita asked me to give this talk to you, and she said, talk about earthquake geology. Okay, so that's what I'm talking about, earthquake geology. A little bit different than seismology. You know a lot more about seismology than I do, because geologists look into the past. So we're trying to understand the pattern of earthquakes in the past. You get to worry about the earthquakes in the present. And so some of the things that I'm going to tell you about has to do with the way in which when we have understood how earthquakes are formed and how they have affected us in the past, so that you can be ready for the future. I am going to be speaking in English because my Indonesian is limited to ayo, salam alaikum, and something else that I forget right now. So I will try to speak slowly so that you can follow me. I also plan to talk for about an hour, and then I want to hear from you. I want you to ask me questions about geology, about Mexico, about California. Anything you want to ask me, I will be glad to answer. If you don't ask me questions, then I will ask you questions. So you want to be the ones asking the questions. All right, let's take the next one, please. We're going to talk about earthquakes, and of course, everybody knows what an earthquake is, right? It starts moving, and you are afraid, and you run away, half-dressed. But what exactly is an earthquake? How are they generated? Next. In Indonesia, we know that earthquakes are generated by dragons that live under the ground. And every time the dragon moves, there is mayhem and destruction. If you're in Java, it's not a dragon, it's a snake, a big snake that moves through the ground. And you know, there is a certain folk wisdom about that, because a dragon or a snake moves in a wave fashion. In the Western world, next, we didn't recognize that. Aristotle, that genius of philosophy, sat and thought about it, next, and came up with the idea that earthquakes were the earth having a bellyache and straining, and that's what caused earthquakes. And this is Aristotle, right? So he's big. So for 2,000 years, we didn't make any advances on earthquake science. It was not until the Renaissance, next, that one of the Renaissance scientists or polymaths thought, well, no, it's the earth being sick. You know, Aristotle said that. But the earth is kind of in a bed with layers, and every time it passes gas, there is waves forming. And so finally, the Western world caught with the Indonesian wisdom that says that an earthquake, next, is the passage of an elastic wave. It's an elastic wave moving through the ground, and that's what causes the earthquake. Well then that opened our minds. But the next question, is what causes the earthquake? Now this is an image of a famous earthquake that happened in 1883, I think, in California. And this poor guy that lived there, of course this is not from 1883, this is many years later, but this poor guy was having a bad day. Not only had the whole thing moved, but these cracks, these breaks of the earth had caused him to lose his home. Now what came first? The earthquake, and that cracked the earth, or the breaking of the earth, and that caused the earthquake? Next. It's a question similar to what came first, the chicken or the egg. In order to get an egg, you need a chicken, but in order to get a chicken, you need an egg. For the longest time, we thought the earthquake happens first, and that breaks the ground. And it was not until the late 1800s, 1880 or something like that a Japanese seismologist thought, what if it is all the way around? What if it is the rocks breaking that generate the earthquake? Now, he was just thinking out of the box. He had no evidence whatsoever. It was not next until the 1906 San Francisco earthquake that we finally got the evidence we needed. Now, this was a devastating earthquake that destroyed the city of San Francisco. And Congress, which is on the other side of the United States, in Washington, like you're going to have your capital in Borneo, imagine what is happening here in Java. So the people in Borneo are going to say, okay, go to Java, make sure that doesn't happen again. And so they gave the money to a very good geologist, W.H. Reed, to go to California and make sure that no more earthquakes happen in California. Well, it was not going to work. But he had money, and money is good. Next. Because, well, let me backtrack a little bit. When California became a part of the United States in 1850, there was gold discovered, and there was great development in San Francisco. And in 1889, there was a map done. This was a beautiful map of the whole San Francisco Peninsula done by the best geographers of the United States. And then it started growing, and people went crazy, and new buildings were done, the port was increased. Next. So a second map was done in 1882. So 1869 was one, 1882 was the other one. There had been 13 years in between. Next. And what they found is that the distance between the red point on the north and the red point on the south has changed. In 18 years, the points have moved apart by a lot, by a meter. And the same was true between the points in the middle and the point in the very bottom. Now, a meter, that's too much for a geographer, for a good surveyor. I mean, they can come within the centimeter. How come they were so wrong? And then the other odd thing, next. Oh, okay, well, this is the earthquake. Let's go back one. The other odd thing is that the distance between the 2 points in the center, next. No, it's exactly the same. Okay, was the same. So in the north, the distance had changed. In the south, the distance had changed. But in the center, it was exactly the same. So then came the 1906 earthquake. Next. Oh. No. Okay, back. 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 Okay, so now comes the earthquake. Go, forward. The whole thing is destroyed, right? So Reed comes back with lots of money and orders a third survey, a third topographic survey. Next. And so, for the third time, a map was created, and then something really strange happened. Next. The distance between those center points had changed by 2 meters. And he knew why, because there was a fence, and the fence had been cut by the fault. So there was a clear explanation of why it had changed. Next. Back. Sorry. But the distance between the north and the south points, and the center and the south points, was back to what it had been in 1869. And that gave Reed the idea that earthquakes are generated by elastic rebound. It's the elastic rebound theory of earthquake generation. Next. Basically says that if you have two portions of the earth and they are trying to move in opposite directions, next, some of that work done by the tectonics is stored as elastic energy in the rocks. And that's what happened. The points were getting farther apart because the rocks were being bent by that process, until eventually, next, you get the earthquake as the release of that elastic energy. Now, the points on the sides have gone back to what they were, but the points along the fault were broken. So we learned that it's the breaking of faults that causes earthquakes. And from there on, we could concentrate on the faults. Next. Now, I was lucky enough to have the company of Dr. Swaidi Ahadi from the Padang yes. And he traveled with me, and so we were able to see the West Sumatran fault. And there are many similarities between the West Sumatran fault and the San Andreas fault. It's a very different tectonic regime because, you know this, right? There is a subduction zone off the coast of Sumatra. But there is also a big fault like the San Andreas fault. Now within this fault, you have segments. You can see the little lines. I drew that. There are better maps than that. I was just in PowerPoint drawing the lines. But you notice that between the bottom segment and the middle one, the fault steps to the right. And between the middle one and the top one, it steps to the left. And then there's a final step right there, just under the word north, in which the fault steps to the right. Now what happens next is that when the fault steps to the right, then you have a depression formed. It's what we call the pull-apart basin. The block on the left is going north, the block on the right is going south, and the area in between opens. That's, for example, the Turutung Valley. Thank you. I told you I didn't do Indonesian. And that's why it is such a flat, nice agricultural area, because it is opening apart. Now, Lake Singharak is similar. The reason why Lake Singharak is there is because the fault takes a step to the right. Next. In contrast, when you're in the middle, the fault steps to the left. Now imagine, the block on the left is trying to go north, and the block on the right is trying to go south. So it scrunches the area in between and creates what we called a transpressional regime. The mountains get crunched. There's mountains there in the little diagram on the right. There are mountains in central Sumatra. And the river, which I never can remember the name, cuts deeply through them, forming a gorge. Next. The reason for this strange combination of subduction and West Sumatran fault is that if you're in Jaffa, the subduction is happening at right angles, right, face to face, right? But if you're in Sumatra, because Sumatra has a different orientation, the subduction is sideways. And that sideways is what is causing the West Sumatran fault to move. I don't have it here, but I'll show it you in a moment. There is a very good paper about the West Sumatran fault that I will recommend to you in a moment. Okay, next. So this is a paper by Robert McCaffrey, the tectonic framework of the Sumatran subduction zone. By the way, this presentation is in your computers, so you're welcome to make a copy of it. You're welcome to take a picture if you want, but I'm not taking it away. It stays with you. Okay? And that's an interesting diagram up there because you can see the subduction and the little red stars. That's your problem. That's the subduction related earthquakes. But you get a double whammy because the West Sumatran fault with its little shallow red stars is also a source of earthquakes. Pobrecitos, you got it two ways. You got it associated to subduction and associated to the strike slip fault. Next. In California, we have our famous San Andreas fault. And the San Andreas fault starts down there in the right and goes through one of those transpressional regimes where the yellow circle is. That's where Los Angeles is. There hasn't been an earthquake there for 150 years because the rocks are fighting, they are deforming, they are not being able to break. So that's a major source of concern for us. And then in the northern part, you see the blue circle. That's a transtensional basin, similar to that valley that I couldn't pronounce, Taratung or Taratung. That's where the famous Silicon Valley of California is located because it's a nice flat area with lots of space. So in many respects, the San Andreas fault is similar to the West Sumatran fault. But we don't have subduction there. Our subduction is on the north where you see the blue triangles. That's where we get our subduction-related earthquakes. So we have them separated, but in many regards, we are not unlike Indonesia. Next. Now, how big can the earthquake be? Well, you can measure it, but how many people went out half-dressed? But in reality, an earthquake is mechanical work. It's the work that you learn in physics, like pushing a big box. It's the force that is applied times the distance. That's the definition of work in physics. In the case of a fault, you can imagine that the two blocks are moving along an area represented in red there. So if we can estimate the force and the distance, then we could calculate the energy. Or we estimate the distance and the area, and then we can calculate the force. And that would be the equivalent to the energy. In seismology, what you do is you integrate either the acceleration record or the displacement record. But for all old earthquakes, like the 1906 earthquake, we don't have that opportunity. So we have to go at it the long way. We need to calculate the area of breaking, the amount of displacement, we know that. You saw the fence, 2 meters. And we need to calculate the shear strength of the rocks. And that's what we do. We take that M0 is length times depth, that's the area. Little d is the displacement. Mu is the shear strength, and big D is the displacement. Once we have the work done, the moment, then we plug it into the equation in the bottom, MW, the W stands for work. It's the magnitude due to the work done, and calculate that logarithmic value, and that's the 6.4 that you are familiar with. This is the way in which geologists reconstruct what an earthquake may have been in the past. Now, you can imagine that to measure the distance, we have to do a lot of work, a lot of kicking of rocks. That's what Professor Gayatri does in in Yogyakarta University. She cuts trenches along the trace of the fault, see what units have been displaced, establishes a date, and in that way she can distinguish different events. Next. Now, this is the San Andreas Fault. And this is the San Andreas Fault seen by the side. So we have taken half of California away, and we're seeing the San Andreas Fault as if it was here in the blackboard, right? Every dot is an earthquake. Now you notice that there are very few earthquakes close to the top. That's the brittle zone of deformation, so it cannot build that elastic force. Then in the middle, you have the zone of elastic deformation. And what is important here is to notice that it goes from about 1 kilometer to it's in miles, from about 1 mile to 12 miles. So say 20 kilometers, that's where the fault breaks. And then below that, of course, the fault continues, but it's in the zone of plastic deformation, and it cannot build the stress. So we have a way of telling how deep the earthquakes are. They are between 1 and 20 kilometers. Now notice that in the left there in gray, we had a gap. That was an area where there were no earthquakes, and people thought, oh, okay, we're safe in there. No, it was just waiting for another earthquake, and that happened in 1989 with the Loma Prieta earthquake that nicely fills that space. In the Loma Prieta earthquake, the big quake, the main shock, was at the bottom, was at 20 kilometers depth. And from there, the break propagated upward, like a fan. Have you seen when a pebble hits the windshield of a car and creates a spray? That's exactly what is happening there. And the reason why it's at the bottom of the zone of elastic deformation, because that's where the rocks can deform the most and accumulate the elastic energy. Next. All right, so now we have some correlation between the depth of the fault and the length. That's the area that we're concerned about. And a couple of scientists measured many of the different places where we could estimate the magnitude of the earthquake and measure the length of the fault, and came up with that equation down there, which for you it's going to be it's a logarithmic equation. But now, if you know that your fault is 20 kilometers long, you go to the 20 and go up to that line, and you read that the maximum credible earthquake on that fault would be 6.5. So this is the way in which we geologists complement what you are doing. You're doing the recent stuff, we're doing the old stuff. Next. And so, I know that you have done this for the West Sumatran Fault because I have seen it. For the different segments, you can estimate what the likely magnitude of a credible earthquake would be. Now, of course, it should not be less than what we know, right? So, for the Opak Fault near Yogyakarta, we cannot see the fault, but we know it can generate a 6.4 earthquake because it has happened. So never assume less than what we know has happened. Next. That table is somewhere there. Okay, the second measure of earthquake strength is how much damage it has caused. We call that the intensity, and it used to be the reports, oh, the dishes came out of my shelf, or the chimney fell off, or the tree toppled over. But we don't do that anymore. It took forever to find out what was happening. Imagine this happened in Sulawesi. It would take days to collect the information. So now we use our cell phone. Next. No. Next. Oh, before I go there. Here's two famous earthquakes in the United States. The red is bad destruction. On the left is the 1906 San Francisco earthquake, and on the right is the 1810 New Madrid earthquake. Now, which one was most destructive? What do you think? The one on the right, right? Because it covered a much larger area. Right now, there is, of the 300 million people that live in the United States, half of them live in that area. So that would be the most damaging earthquake that we can imagine. The 1906 earthquake was bad, but why was it so local? Notice, it wasn't even felt in the neighboring state of Nevada. Next, it's our faults. We have many faults in California, and the faults act as mirrors. So when the when the elastic wave comes in, it comes, hits a fault, and bounces back. That's bad for the people of San Francisco because they get it like if you were playing a gong. But it's good for the people of Nevada because they don't get to feel those earthquakes. So geologic conditions are very important on the type of shaking that you're going to get at a given place. Next. Oh, no, that one. Perfect. Of course, in terms of destruction, one of the big things is the house falls on you. Right? Now, houses and buildings are built to be vertical. Like us. You can jump and you don't crumble into the ground because you're to be vertical. But you're not built to be sideways. If you stand here and I push you sideways, you're going to tumble over. Same thing happens with buildings. So what is most important is not the vertical force, is the lateral force. And that is what the civil engineers need to know in order to design good buildings. Sometimes you kind of cut in the concrete or use thin rebar. Not good. Not good if there's going to be a strong push. Next. Now you can use your cell phone. Your cell phone has a built-in accelerometer. Next. And so that little chip in there, next, records what the acceleration was in the X, in the Y, and in the Z directions. And again, the X and the Y are the most important ones. Okay, so I don't expect you to leave your cell phone here to wait for the next earthquake. But that chip is so cheap, so easy to install in a building, that now lots of buildings have those acceleration records. And we're slowly collecting the information that we need for strong motion acceleration. Next. This is a very typical acceleration record. And you notice that it has a high value of 1.5. That's the peak ground acceleration. That's how fast 1.5 Gs happen. Now, a civil engineer will tell you, I'm not going to design to that. That happens only once. Give me the repeated horizontal acceleration because my building is going to have to withstand it 2 or 3 times. And we have looked at a lot of these records, and we have found that it's about 2/3, about 68% of the peak ground acceleration. So when we tell you what the peak ground acceleration is, calculate 2/3, and that's what you want to design to. Also, it's not the same to design a little house or a tall building. So the civil engineer has to choose an acceleration record that has the frequencies that are important for the building. That's the civil engineer. We're geologists. We'll tell you what the ground does. What you want to put on top of it, that's your engineering design. You get to do that. Next. So we have collected peak ground acceleration in many earthquakes, and we found that if you plot distance in a logarithmic scale versus peak ground acceleration, it falls off. The farther you are from the fault, the less the peak ground acceleration is. It's not perfect. You notice that the lines are different, whether it is rock or soil, and there is a fair amount of scatter. So in order to do good design, you take the mean plus 1 standard deviation to cover most of the conditions. Next. You need to be aware that the frequency of acceleration is going to be different in rock than in soil. So that's where you also need us, because we need to tell you what type of soil you're building on. You may have heard about the microzonation that you do that you have here in Indonesia. That's what it's talking about. It's trying to figure out what the different soil thicknesses are. Next. How do we use this? Okay, this is California. These are the faults around San Francisco. And you notice that they have different sizes. They're slightly different types. We don't know when the next earthquake is going to be. We're not magicians. But we can tell you that if the red fault breaks, it is likely to generate a 7.2 earthquake. And knowing that as you move away, there's going to be less acceleration, we can figure out where destruction is likely to be highest and where destruction is likely to be lowest. Next. Take, for example, an earthquake along the Hayward Fault. The black and red is total destruction. So the people that live there will not be able to help themselves. The police stations will be destroyed. The fire brigades will not be able to operate. So in that scenario, what we do is we bring help from the west side cities, and they are in charge of coming to Hayward and doing the relief work. Next. If on the other hand, the earthquake is along the Greenbelt Fault, then the city of Livermore is going to be destroyed. They're not going to be able to help themselves. Now Hayward has to come and help them. So in all these cities, in the fire department, in the police department, there are binders that say, if Hayward fault, this is what we're going to do. They are prepared. Preparedness is the best way to defend ourselves from that type of damage. Now, again, we're not guessing when it will happen. You cannot guess that. But if it happens, we know what we're going to do. Next.
Where is your house?
My house would be on the right edge of that figure. Yeah, I live in the agricultural area of California. Remember the mirrors that were there? When the 1906 earthquake happened, it was barely felt where I live. So I'm protected by all those faults. Next. Now, this is from that paper that I showed you. This is the subduction zone. A lot more difficult to deal with because you cannot see it. And so in this case, the blue patches are areas where no earthquakes had been recorded by the time they did this. So we imagine those are locked portions of the fault, and the highest risk probably comes from those areas. I don't know much about it, so I'm going to let you refer to that paper in order to understand how they do that. Next, please. The best protection is good construction. And so in the United States, we have the International Building Code. You too, you have it here as well, but we follow it. You, not so good. You normally follow the building code for the big buildings, but most people that build a little house, they don't worry about that. You know, they just hire the masons, and the masons have done it enough. But that's a problem because the mason doesn't know what the ground is like. Next. So one of the things we do in the International Building Code in the United States is we have general risk areas. For example, I live in that number 3, and for each one of these risk areas, next, we have a certain number of parameters that we use to design the buildings. And you notice there that they are divided by soil profile type. You cannot read it, it's too far. But it makes a difference whether it is soft soil, stiff soil, thick soil, thin soil, rock. And how are we going to know what that is? Well, we could drill, but we can ask the geophysicist. Next. because geophysicists can use seismic refraction to determine the velocity of the soil, and the velocity of the soil is a measure of the strength of the soil. So that's what we normally do next, particularly using the technique of refraction microtremors. The little cups are geophones, and you don't have an explosion, you just wait for the noise of the city to sweep through the geophones, and from there you can determine what the velocity of the soil is. For example, this is Las Vegas, next. And there is the shear wave velocity profile determined there. You notice that from the surface down, it increases. That's common because the soil gets more compacted. But in this particular case, at a depth of 140 feet, you have a reversal in velocity. It means you have a soft layer of soil at depth, and those are the ones that normally cause problems. Next. What are we going to do to protect society? Next. Society is not very smart. They like to build their houses right on the fault. So in order to avoid that, we have a seismic protection program. Next. And it starts by knowing your faults. The one thing that we want to make sure is that we know if a fault is active or old or dead. And in California, we have a rule. The fault, in order to be considered active, must have moved in the last 11,400 years, 700 years. Now, how crazy is that? Why 11,700? Why not 50,000 or 10,000? No, it's a very precise number. Well, again, that's geology. In California, between 15,000 and 11,700 years ago, we had what we call the pluvial period. It rained and rained and rained and rained and rained, and every single fault was covered by a lake. Next. So now we know when we look at the fault, we go to the places where the little lakes either are or used to be, and we cut a trench. Now, in lakes, you have very distinctive lake deposits. So if the lake deposits next are not caught by the fault, then we know that fault has not since the pluvial period, and we can be pretty certain that it has not moved during the last 11,700 years. On the other hand, as in the right, if the fault cuts through the lake deposits, then we know it has moved over the last 11,700 years. And every geologist can recognize lacustrine deposits. So this is a geology-based determination on the age of the fault. And then we go whether the tectonics is right and all sorts of other things that we do. But this is the fundamental one. Now, I don't know what the climate has been in Indonesia for the last 10,000 years, but the climatologists may be able to tell us if there was a pluvial period or not, or a dry period, and you would have to determine what the right number for your active faults would be. So I'll let you have that as homework. Determine when the pluvial period might have been in Indonesia. Next. In Indonesia, you cannot see a thing. There's plants all over the place. It's very hard to do geology. But you have Google Maps, and you have LiDAR. And I know that BMKG has a LiDAR drone. And with LiDAR, you can see the shape of the land. It's very important when we look at the shape of the land to recognize things like linear valleys, scarps. Sometimes you have a creek that comes, takes a turn, and then continues. That's because the creek has been moved by the fault. So geomorphology, as a branch of geology, is a very important thing for you here in Indonesia. The type of fault is important. This would be the West Sumatran fault, for example. Next. But if you are in Siberut or islands, in one of those islands, you have reverse faults. You have compressional faults. And those are a little harder to identify because the moment they run over, they slough off. And that's what these diagrams show, the different morphology of those type of faults. Next. Eventually, Oh, and that's a different type of fault. That's a normal fault. That is found in the East Sumatra region, where you have tensional areas. That would be the next. The typical pattern of faulting there. Another one. And depending on how it has degraded, it will look slightly different. So you need to have a good eye for those type of things. Next. Ultimately, you need to cut a trench. You need to get a backhoe, cut a trench, and this is an example of a reverse fault like the ones you would find in Siberut. Next. And the key, what we're trying to do here is to find exactly where the fault broke and try to determine when it broke. Our main concern is to try to find those faults that are still active. Next. In California, we have many faults. Next. And so we have started a program in which every fault has been mapped by good geologists. We know exactly where it broke. We kind of know when it broke. And we have covered the whole state this way. Next. So each one of those little squares is one of those very detailed maps where we know exactly where the faults are. We definitely don't want to build anything on top of the fault. So if this building were to be on top of the fault, we move it that way and we move the sports field here. Because it doesn't matter if the sports field gets cut, right? We cannot lose the building. That's the important thing. Next. Another thing that we're concerned about is slope stability. Next. Sometimes if you have a deep slope and it shakes, then the slope would come down. And so we know roughly what the strength of the rocks are. We can calculate the slopes using GIS. And in that dark blue color, you see areas that are likely, that could fail. And before we authorize a building permit there, a geologist has to go and assess the stability of that particular block. Next. The other problem we have is liquefaction. In California, this is a problem because of the strong seismic shaking. I think in Yogyakarta, you also had some cases of liquefaction. Liquefaction happens when you have clean sands, no clay, shallow groundwater, and you give it a good shake. Because that increases the pore pressure of the grains. They separate and they lose their shear strength. Next. So we have the similar map. Now it's the green color on the left. Those are areas where the soils are susceptible to liquefaction. Now we also have rivers like the Opak River, and you can see that if the ground loses strength, it will shift toward the river. And I think that's the main problem that they had in Yogyakarta. Because of the Opak River, the city kind of took a little step toward the river, and that damaged the foundations. This may, one more time, one more slide. This is the liquefaction potential damage or liquefaction susceptibility map for San Francisco. So if you want to build something in those red areas, you need to have a geologist come, look at the ground, maybe do some surface geophysics to determine whether there is a clean sand with shallow groundwater in there that could be affected by liquefaction. Next, this is my very last slide, I think. I want to thank the director of MKG, Professor Di Currita, for inviting me to go through the country and to come and talk to you. Ibu Cristiana, the chief of the Silangit Meteorological Station, was very generous with her time and her assistant. Dr. Swaidi, the chief of station of Padang Panjang, that's a geophysical station. He was wonderful accompanying me. And of course, Professor Suko and Professor Maman, who have welcomed me here to talk to you. I am delighted to have that opportunity, and I look forward to chatting with you. Thank you.
Thank you, Professor Ferris. And now we have Dr. Suko, our director behind. Please, Dr. Suko, maybe we can come to the front of the stage.
Glad to see you again. No problem. No problem.
Okay, maybe we can continue to the question and answer sessions. Okay, if you have any questions, just raise your hand. Okay, 1, 2, 3. Okay, we start for 3 questions first.
Thank you for the opportunity. Professor, first I want to introduce myself first. My name is M. Esperanza from Geophysics Major in second year. Actually, I have 2 questions, if I may. The first question is, what causes gaps in seismicity such as San Francisco, Lama Prieta, and Battlefield Gap along the San Andreas Fault? And also the mechanism of how can a fault act as a mirror for earthquake? Thank you.
Okay.
Muchas gracias, professor.
So the first one has to do with the Loma Prieta earthquake. The whole San Andreas fault is under stress, but it doesn't break all at once. It breaks in segments. And the Loma Prieta segment had been stuck. The forces were accumulating there, and we thought, oh, this is safe. We should have known better that it was just a matter of building the stress. Why it was stuck, that's an interesting question. Probably because we were extracting groundwater. And so the pore pressure in the rocks was very low, which allowed them to build more and more stress until they broke. Does that answer your question?
Yes, sir.
And the second question was?
How can fault act like a mirror, for example, in 1906 earthquake in California?
So remember that an earthquake is an elastic wave. It's a mechanical wave. When that mechanical wave finds an interface, either I can go through it or it can reflect. It could refract as well, I guess. I think that what happened is because the faults have a lot of clay in them, their impedance is very high. And so they acted more as a reflector than as a translucent medium. But I don't know, really.
Thank you for the question, the answer, sir.
You're
Just
welcome.
gracias.
Okay. Thank you. Good questions. Another one?
For Mr. and for everyone. So I want to ask one question. So many big companies was built their central office in the California, like Apple, Google, and Meta or Facebook. So even the Hollywood celebrities was built their house in California. So we know that California is the most active state in the United States, even in the world. So what aspect can BMKG or Indonesian government can apply according to the government of the California to in way to the aspect of the earthquake early warning system? Thank you.
You touch on 2 of my nemesis, of my demons. First of all, people live in San Francisco or in Los Angeles because it's beautiful. And they figure, I'm going to be here for 30 years. If it's not going to happen in the next 30 years, I'm going to enjoy a beautiful area and run the risk. Now, me, I live in boring Central California in agricultural land. I don't have to worry about it, but it's not as beautiful. People are risking, are running the risk. So they are gambling. And for that, there has been a whole branch of seismology that worries about the probability of an event happening. It's probabilistic seismology. I don't like it because it's like, I ask you, what do you think is the chance that the West Sumatran fault will move in the next 30 years? And you said, I don't know, 10%. And I asked you, and you said, I don't know, 50%. And I'd say, well, I say 20. So 10, 20 is 30, and 50 is 80. Let's say 40%. That's a guess. That's a combination of your guess, and my guess. And honestly, I don't want to spend a lot of money building something based on a guess. Now we have the early warning system. The early warning system, I lived it in Japan because I was there having lunch, and my cell phone picked, ding, me and 20 other people picked the cell phone, and it said, there is going to be an... There was no time to do anything. Yes, they told me, but I couldn't even say, God protect me. There was not enough time. And then a week later, I was there with myself. Oh, and I thought, I really should have measured the time, right? How long? I think it was 2 or 3 seconds. There was another one, so I pulled my cell phone and measured the time, and okay, 5 seconds, 10 seconds, 20 seconds. It never came. It was a false alarm. So the problem with warning systems is, if they're going to work, they have to be reliable. They have to have very little false alarms, and there has to be enough time to do something. For example, in the United States, in California, they are selling this. You can buy an early warning system, and most of the people buying them are the police stations and the fire stations, because they figure 2 or 3 seconds may be enough to open the gates. Even if everything else gets destroyed, at least they can get the vehicles out and provide help. But I don't see it changing the way people live, to tell you the truth. You can say, hey, Mom, we're gonna... and that's about it. Okay?
Thank you very much, Mister.
You're welcome.
Thank you. And I see another questions from
You
that
had a
side.
question back there, I think.
Good morning, sir. A great honor to me that given a chance to ask the question in this moment. My name is Lutfi, and I would ask 3 questions. First question, as we know that Kalimantan isn't so prone to an earthquake occurs, is there any possibility that in a few years next, that will be an earthquake sources in Kalimantan like Maratus cases in the past deformation geologically, sir. Number 2, the peak horizontal ground acceleration, I see that approximately 65%, and I don't know what is it. Number 3, about the structural seismic design manual, I'm interested about the Tohoku Japan that I've ever seen for a video recording in the internet, that in Japan, especially in Tohoku, there was so many building destruction. What causes this, sir? As we know, Japan has incredible technological seismology. Thank you, sir.
Thank you. Remind me again of the first location. Were you asking of California or Indonesia?
Indonesia, sir, Kalimantan.
Indonesia.
Borneo.
Dr. Suko, you and I need to go to Borneo and to the Celebes, because you have been there, you know this better than I do. It is, if you look at the fault map of Borneo, it looks a little bit like a grate, like a fence, one way and the other. And normally those are associated to areas that are under compression, big compression. I suspect that the pattern you have in Borneo is because you have subduction in Indonesia and you have subduction in Philippines, and Borneo is caught in between, like you're cracking a wall. If we cannot see the faults, then it's going to be up to you, the geophysicist, to locate little events and make sense of them. I think one of the major advances that you can do is do what we did with the San Andreas Fault, is create the plane of the fault and put your centers there, because that will tell you how deep they are. You have also focal mechanisms, so you will be able, my guess is that there's going to be oblique movement there, so you will be able to distinguish those events. Can you do something with that? You could do the same thing of calculating peak ground acceleration given the area of the faults. But my first step would be to locate the hypocenters on the plane of the faults, try to determine how long and how deep they are. The peak ground acceleration, that 65%, comes from the analysis of many accelerometer records. Basically, there's always a peak. There's always one that is really big. And then we look at something that is repeated 4, 6, 8 times. And that's what the civil engineer needs, because that's the one that is going to move the building this way, and that's when the buildings fail. And remind me of the third question.
About in Tohoku, Japan, there's so many destruction buildings that, as we know, that Japan has the technology about seismology is incredible.
Well,
What the impact, what the effect, what the causes are?
I am a little surprised because Japan loves concrete. They will put concrete on anything. They don't go a little layer of concrete. They put a big, thick layer of concrete. Now, what I know is that the buildings are extremely sturdy. But if the ground liquefies, then the building goes sideways. Now, you talk about a lot of destruction. If that was collapse, then that is a failure of the design. One thing that happened in Yogyakarta is there was a lot of failure of small houses. And that's probably because the columns were under design. They maybe used 5 millimeter rebar when they should have used 10 millimeter rebar. They use low strength concrete when they should have used high strength concrete. And that's because most users say, no, don't give me the Cadillac. Having said that, I must confess I am not familiar with the destruction in Japan that you're referring to.
Excuse me, here,
Thank you so much, sir.
some comments here.
Mau menambahkan, Sir. Izin Pak Suko mau menambahkan. Tadi kan, oh ya, perkenalkan, nama saya Irfan Fatarwin Lubis. Saya asistennya beliau, Pak Profesor. Tadi pertanyaan pertama, potensi gempa di Kalimantan ya, terutama di dekat dengan ibu kota baru Nusantara. Selama kita tinggal di Indonesia, itu pasti kena gempa, terutama di Kalimantan juga. Di daerah timur Kalimantan, itu kan ada potensi minyak ya. Teman-teman tahu kalau minyak, produksi minyak, itu pasti memanfaatkan jalannya sesar, supaya hidrokarbonnya bisa keluar. Jadi kalau kita lihat, apalagi dari BMKG, gempa itu jarang terjadi di Kalimantan, tapi ada, potensinya ada. Nah sekarang adalah gimana cara kita mengidentifikasi sesar, struktur yang berpotensi untuk menjadi gempa. Menurut hemat saya, waduh keren banget nih. Jadi menurut saya itu kebanyakan sesar karena Kalimantan, Jawa dan Sumatera dulu itu Sundalen bergabung. Pemetaan yang baik itu pemetaan bawah laut, terutama di laut Selat Makassar, Bapak. Nah itu pemetaan bawah laut itu akan sangat diperlukan untuk mengidentifikasi jenis-jenis sesar yang ada. Dugaan saya itu kemungkinan sesar turun karena dia masih bergabung di satu Sundalen. Begitu untuk tambahannya. Terima kasih. Thank you, Profesor.
Terima kasih, Pak.
Thanks, good
Thank you so
comment.
much, sir.
Very welcome.
Thank you, sir.
We still have many times. Any other questions from students?
There's one back there.
Ari.
It doesn't like you, man.
Thank you for the time. I want to Ari. I want I want to ask to based on based on geological map of Surabaya is Java.
Hello, hello.
Hello, hello. Based on this. Apa nih?
Just speak.
Oh,
You need to be loud, okay?
okay. Based on geological map of Surabaya is Java. There's three types of like three types of soil: sands, clay, and alluvial. Which one is more dangerous in earthquake? From three types soils of that. Thank you.
Well, that's an interesting question. Clays are not very good foundation materials because they have the tendency to compress. But if they are compressed, they can be very strong. And so during the site investigation, the civil engineer will dig holes and will test the strength of the clays. Clean sand is the one that worries me the most because clean sand doesn't have enough shear strength. So whenever I see clean sand, I suspect, liquefaction. Alluvium, great material. Alluvium has enough dirt in it, enough clay, that it has a good shear strength. So if I were to build my house, I would build it in alluvium.
Okay, thank you for the answer.
Thank you.
sir.
Other questions? Okay.
Okay. Good morning, sir. My name is Muhammad Najib Sungtadir. You can call me Najib. I have questions. In the history, we know in Indonesia occurred earthquake, swallow earthquake with modern magnitude. In your opinion, I ask your opinion. Can we say identify surface rupture for the earthquake, for the swallow and modern earthquake?
Can we identify a place that it would be safe, you mean, or most dangerous?
More centers.
Okay. Well, first of all, if you're close to a fault, that's dangerous. If you're in a slope, that's dangerous. If you have a substandard construction, that's dangerous. Now that's where I end. You, on the other hand, you have modeling tools. And oftentimes, in your studies of seismology, you can reconstruct the path of the elastic wave as it moves from rock to soft sediment to stiff sediment. So my geologic opinion would be most dangerous, not so dangerous, pretty good. Then you would need to add your geophysical opinion to that. And then both of us would advise the civil engineer on what is the best approach. I don't build things, I'm terrible at building things because that's their specialty. I think that we need to be careful about that. There is a field of civil engineering that has to do with seismic design. So I would make sure that my civil engineer is up to snuff in that regard. There is no safe place on Earth. If it is not an earthquake, it's a meteorite that falls on you or a typhoon that wipes you. I think the key is adaptation. Recognize what the dangers are and then take the best possible solutions. Education is big. Relief and rehabilitation, what are we going to do to help those people is important. In Indonesia, insurance is not as important. I don't think many people carry insurance. Maybe the big hotels carry insurance. But insurance has proved to be pretty useful in the United States.
Okay, thank you for your opinion, sir.
Thank you.
Okay, now let me ask you a question.
Okay.
Do you study English as part of your program? And Spanish? Ooh. Well, English is very important. You need to speak it, you need to read it. So work on that, because that opens the gate to the world, basically. You can go anywhere in the world and somebody will speak English. You can go to half the world and somebody will speak Spanish. So. Or you can go to the other half and somebody would speak Chinese. So if you need to learn languages, I'd say English, Spanish, and Chinese. Yeah, there's a lot going on.
Thanks again, Professor Ferris. Any other questions? Okay, we still have another one.
Dick, from your presentation shows that the waves that is the most dangerous waves from the building is the horizontal one, not the vertical one, because building is built to
resist the vertical force.
yes, to resist the vertical one. How is that that is matter that from your geological VOV point of view, that how is the horizontal wave is more important than the vertical one?
So you know your waves, right? You know your P wave and your S wave. We use that in seismographs to locate the earthquake. But it's really the surface waves, the ones that cause most of the problem. You have the Rayleigh waves that make you go like this. Imagine you're a building going like this. And you have the L waves, the love waves, that are either moving you this way or moving you this way. Those are the ones that are most problematic, and they're the ones that have the largest amplitude. Now, if I'm a very tall building, one of the big hotels, I like to go like this, slowly like this. So the L wave do not affect me as much if I'm a tall building than if I'm a little building. A little building really has a hard time holding to this sideways movement. So my big concern from the protection of people are the surface waves. And unfortunately, sometimes we don't study them with as much detail because they are very confusing. They are noisy. They go everywhere they want. Civil engineers are used to designing with wind. And there's all sorts of good tools to design for high wind loads, particularly in places where there are typhoons or strong winds. So sometimes you can design the building just with wind, because the earthquake is just going to simulate the effect of wind. I guess that would be, make sure that your civil engineer understands wind. Yes, please. Two ways. I am convinced, I truly believe, that any modern buildings have been built to a high standard and will withstand deformation. But remember that there are many old buildings. You have the same thing here in Jakarta, right? There are many beautiful young new buildings. They're probably okay. But it's all the 10,000 other old buildings, the ones that are going to cause problems. In the United States, we don't have the legal power to say to someone, hey, your building is old, you're going to have to redo it. Unless it's a historical building, then it can be protected as historical. But if it is just the BMKG clock tower, we cannot force BMKG to build it up again because it's a functioning tower. So it has improved the future, but it hasn't done much for the past.
Please give applause to Professor Ferris. Okay. Thank you, Professor Ferris. Probably that will be the last questions from the students. And I will return the time to the Miss Anggun as MC for this event. You can continue, Miss Anggun. Thank you.
Thank you so much, Professor Horacio Ferris, for all the discussion, for all insight to us, such as earthquake divination, theory elastic rebound, preventive steps to decrease earthquake, and many more that I couldn't speak it one by one. Okay, before we close our event, let us hear the closing remark from the head of STMKG, Professor Professor Suko Prayatna Adi.
Thank you very much. Good morning, Professor. Good morning. Yeah, thank you for your coming. Thank you very much for your share knowledge, and you can share your experience in California. And I hope if future, next time, next month or next year, you come here again for the share your new knowledge to my, I call Taruna STMKG. Taruna is student and my university. Okay. I hope I hope you and your university and state colleague, I hope can collaboration. Maybe for the visiting research for my student before finish the graduate, I hope can to visit in your university, maybe 3 months or 2 months for research together with your student, and come back to STMKG and then finish the bachelor degree. And I hope sometime my lecture can visit in your university and research together with your lecture maybe, yeah. Special for Indonesian earthquake and Indonesian tsunami early warning, maybe. Okay, and after finish we discuss in this room, we can continue to discuss in my room for the how to collaborate at university and my university. Thank you very much. Terima kasih untuk hadirin semuanya. Ya. This is very important for you. And professor have suggestion for you. You have to learn an English, Spain, and China. Good. This is a very, very good suggestion. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Thank you, Professor.
Okay. Thank you so much, Mr. Sukovretna Adi. The next session is, we would like to present the ceremonial gift to you for sharing your expertise in the session to Mr. Horacio Ferris.
I want to add that you look extremely handsome in your uniforms. Notice that I also wore kind of formal Indonesian shirts and the hat, because I am very proud of being here with you, very grateful. And yes, I will come and visit you again.
Thank you. And maybe the last, we will have photo sessions. So tarunanya tiap angkatan maju satu-satu ya. Tingkat 4 dulu. Iya. Per angkatan ya, tingkat 4 dulu.
Tingkat 4 dulu perangkatan.
Ya.
Di belakang, di belakang, di belakang. Ayo cepat ya, tingkat 4, perangkatan ya. Ya. Itu dosennya.
Pak Puji, Pak Fadlan bisa maju ke depan, Pak.
Dosennya ke depan. Lecture.
Mohon izin, Pak.
Ah, dosennya di tengah, kalian minggir. Ah, dosen di tengah. Oke, yang lain, ya, minggir, miring, jangan kena semua. Miring.
Oke, senyum ya, smile.
Ya. Tunggu. Smile ya. Oke. Hitung.
Smile. 1, 2, 3, smile.
Oke. Good.
Once again. 1, 2, 3, smile.
Ya, thank you.
Oke.
Gantian.
Tingkat 3.
Tingkat 3. Oh, tingkat 2 ya.
Tingkat 2.
Tingkat 2. Ya. Police. Police. Police for student. Student police. Ayo, cepet ya, agak cepet. Agak miring. Yang tinggi di belakang, yang agak kurang tinggi di atas. Dibagi. Bisa nggak agak miring gitu? Masuk semua ya? Jangan masuk semua. Yang tinggi di belakang.
Ayo dirapatkan lagi. Oke. Siap-siap. 1, 2, 3, smile. Once again. 1,
Oke.
2, 3, smile.
Good.
Oke.
Tingkat 1.
Tingkat 1.
Ayo. Ya, terus masuk semua ya. Diatur ya, seimbang kanan kiri. Ayo, enak. Yang semua masuk, yang cewek depan lah. Ayo. Diatur. Tunggu, biar siap dulu semua deh. Ayo semua ya, diatur. Oke, diatur tingginya. Masuk semua ya. Oke.
Oke. Siap-siap. 1, 2, 3, smile.
One more.
Oke. 1, 2, 3, smile.